So moving into section 6.2, what we're going to be looking at is the law of cosines. And I'll say the derivation for the law of cosines is a bit more involved than the law of sines was. Here we're going to have to do a little bit with the distance formula. We're going to see a taste of the Pythagorean identities again. And it's going to take a little bit more thought, but we'll end up to a similarly useful place. So first, we're going to think about what a general oblique triangle would look like in rectangular coordinates. So we'd have a shape something like this, with points A at the origin, B at coordinate C0, which I understand looks weird, and point C at XY, where we say length B is from A to C, length A is from C to B, and length C is from A to B, with Y as the height. Yeah, I know the notation's a little bit confusing, but we'll see why it helps eventually. So here, if we want to think in terms of our trig functions and that inside right triangle, that right triangle generated using the altitude, we can say that cosine of our angle A is going to be equal to x over b, while sine of that same angle A is equal to y over b. And that's not very useful in itself, but we can use this to get something in terms of x and y. That is, we can say x here is equal to, let me get my hand a little bit straighter, x is going to be equal to, b times cosine of A, and y is equal to b times sine of A. And in and of itself, that doesn't seem very useful, but we can take that a bit further, where we can look at that distance A from point C to point B, and have that, since we're going from xy to C0, the distance A can be defined in terms of the distance formula. That is, the square root of the square of the x change, x minus c squared, plus the square of the y change with, in this case, a value of y minus 2 squared. That's nasty, it'd be hard to pull apart, so we're going to square this whole thing and it'll make our picture a little bit nicer. We'll get a squared is equal to x minus c squared plus y squared. And then we can take these parts and make a substitution to put it in terms of our angle A, because I got x's and y's, they don't really mean much, but our angle A now, that's where the real money is. But what we do there is we would have b cosine of A, like so, minus c quantity squared, plus b sine of A quantity squared. Now, the second term is not so bad. There's not a whole lot to do there, but our first term is going to require a bit of foiling. So we're going to have that first term squared, b squared cosine squared A, minus 2 times the product there. So we'd have minus 2b, oh geez, this looks a little bit weirder than I thought it did. 2bc cosine of A. It looks nicer in type because, I can put in italics, I can italicize that C to put that in there. Otherwise, no, it just looks like Bacose. It's just weird. But anyway, we have that. And then we also have a negative c squared, which becomes positive c squared. And thankfully, the other term's not so bad. It's just b squared sine squared of A. Woof. But, nasty as this looks, we can take the terms like this and pull them together and factor out a b squared, where what we would have then if we group is b squared times cosine squared of A plus sine squared of a, which hopefully is a familiar value in terms of the Pythagorean identity. That's actually just 1 written in a long-winded way. Then we've still got a c squared, and we've got a minus 2bc cosine of, oh geez, that's too many c's, a. And then, like I said, this is just 1. So really, this is just b squared plus c squared minus 2bc cosine of a. That is a squared equals b squared plus c squared minus 2bc cosine of a. And if we made our altitude in a different way, we could just as easily get that b squared is equal to the other two, a squared plus c squared minus 2ac cosine a. And those c's, they just throw off my instincts. And then we would also have that c squared is equal to a squared plus b squared minus, oh, excuse me, that should not be an a. That should be a b. These angles should match up, excuse me, minus 2ab cosine of c. Cosine of the angle c, not the distance value c, to be extra clear, just in case. Where these three values here, these three equations, are what define the law of cosines. So it's a bit more work to get the law of cosines than the law of sines was. And it's not quite as nice of a relationship between a, b, c, and the cosine values. We can still use this in the same way that we did the law of cosines, where for these, the cases that we can solve for the oblique triangles are ones where we have a side, an angle, and then a side where the angle is in the middle. Or we can use this if we have all three sides to get our angle measures. But that's what we're going to see in our next examples, is how we can actually apply this not very pretty at the moment mess of terms.